Thank you, guys. I'm really excited to be here. Talk to you about bringing star power to Earth. And yes, we're absolutely going to talk about fusion within this facility. So Lawrence Livermore National Laboratory is one of 3 weapons laboratories in the United States. We're responsible for the nuclear weapons stockpile. So it's kind of one of those little known facts. You won't hear much about us because of the type of work we do. We're located in Northern California, kind of looking due west. San Francisco's out in the distance. The laboratory itself is about 1 square mile. And the National Ignition Facility, which I'm going to be talking to you about, is in the lower right-hand corner. Our programs support key laboratory missions. So the Livermore Lab's about $1.5 billion a year enterprise is what we get funded for doing research and development. We do work in national security, energy security, basic science, and economic competitiveness. Our laboratory really works on grand challenges that will make a difference for our country and for our world. So that's the kind of work that we do. When I'm talking about a project, projects will always exist for a specific reason, right? And there's objectives that you're going to need to meet with a project. So if you think about the fundamental missions of our laboratory and you say, why would we have a $5 billion project there, for example? You go, okay, well, we want to ensure our national security. We want to advance frontier science. We want to build generations of high energy density scientists, folks like you, to come in and work, make sure we've got a future, and to really enable clean energy. So that's where we get to talk about the National Ignition Facility, right? And you mentioned it already, where is the one working fusion power plant we have, which is the sun, right? And fusion is the source of the sun's heat and light. Think about it that way. Slowly moving along. So the question is, could we build a miniature sun on Earth? Right, which was what we thought a lot about when we're building the National Ignition Facility. Primary objective. The word ignition for us means fusion. What are we talking about within the National Ignition Facility? The kind of fuel that we use is a combination of deuterium and tritium. Is the type of fuel within the target system. Our goal is to create a little exciting video here. Really, with lasers, can we take lasers and drive our targets, which are made out of deuterium and tritium, to create the kinds of pressures, temperatures, and densities to have a fusion, actually a self-sustaining fusion reaction in the laboratory? We've already had fusion reactions with the type of work we're doing, but we're looking for the self-sustaining, getting more energy out than we put into the whole activity. The design and construction of the National Ignition Facility. So basic concept of the NIF is to create fusion in the laboratory, and we do that because nuclear weapons work in a fusion regime. How can you study weapons? How can you study to see if they're effective when you don't do any underground testing? The United States has not tested any of its nuclear weapons since 1992. There was something called the Comprehensive Test Ban Treaty, which was never formally signed, but we follow it anyway. So since we don't test our weapons stockpile, how do we have assured deterrent? So we'll do laboratory experiments to create and simulate the types of physics that you would see with weapons. And then we take that data and we run it through very large models and we validate models. And that's how we make a lot of decisions about our stockpile. So that's kind of the how it got paid for part of our mission. We also work in fundamental science, understanding the universe and the cosmos, because that's where you're seeing a lot of fusion activities. So how is that all working? It's also how we pay and got to clean energy and fusion energy. So we've got missions associated with the weapons, with the universe, and then of course with clean energy. The National Ignition Facility is a $3.5 billion line item construction project. So it was authorized by Congress as a $3.5 billion project. It is actually a very large facility. That's over 700,000 square feet. It's about 800 feet long, about 400 feet wide. You could put, I think, 3 football fields on top of that facility. The building itself is quite complex because laser systems have a lot of technical requirements so that they work effectively. but it's actually a machine. You know, I took the roof of the facility off of it so you can see it is just dense packed with hardware. It's a 192 beam laser system. It's a glass laser, meaning the gain that you get for lasing comes from glass. We take glass and we dope it with neodymium, right? And we cut it into sections about this big, so you have a square beam, square laser beams. If you think about it, it makes a lot of sense from density and waste that you get these square beams. We charge up capacitors, right? For about 30 minutes, we take the electricity and we dump it into flash lamp light, and we put that flash lamp light onto that glass, excites the atoms, then we just send our seed pulse through there and we get gain through our system. So it's a glass laser system, 192 beams. We use a wavelength of 1053 nanometers early on in the system, and then we go ahead and wavelength convert to 351 nanometers. We do that because laser light will damage glass, and you don't want to damage glass, but a shorter wavelength couples better with your target. So there's a lot of thought and design that went into our overall laser system. We have energy up to 1.8 megajoules on target, 500 terawatts. These are big numbers. And then the primary wavelength of coupling of the target is 351 nanometers. And we are a good 10 years ahead of any other country right now with our laser technology and with this facility. All sorts of countries around the world are building very large laser facilities because of the weapons impacts, as well as the fact that it's a potential energy source. Now, we'll just do a really brief discussion around lasers. The first laser was demonstrated May 16th, 1960, Hughes aircraft down in Malibu, a guy named Ted Maiman, kind of the granddad. So you go back that far, it's demonstrated, and Livermore Laboratory, of course, was working. Livermore Laboratory came about during the Manhattan Project, so 1950s, 1940s, that time frame. Literally 3 days after Maiman demonstrated the laser, one of our senior physicists, a guy named John Knuckles, proposed to use lasers for fusion energy. So you just think about that for a second. You go, wow, the laser's demonstrated, and boom, 3 days later, let's use that as a way to create fusion energy. So it's a long history. John Knuckles went ahead and became one of the directors of the laboratory, Lawrence Livermore, and has all sorts of really good work that he's done. Lawrence Livermore is the world leader in lasers. We have a very long history of building lasers from 1972, a very small ruby laser, and growing successively over time with increasing of the power and changing the wavelengths. So with large lasers come expertise in systems engineering, systems integration, optics, anything to do with optics. We've got very strong capabilities. Precision manufacturing. Our targets, there's that massive facility, right, 700,000 square feet, but our target is actually only this big, right? It sits in a gold can called a hull room, and inside this hull room is the capsule itself, which is a cryogenic capsule made out of deuterium and tritium. The type of precision manufacturing, there's little tents, little membranes that hold that capsule in place, and those are 5 microns thick. So you end up with very large scale and then very small scale simultaneously. So you have a lot of challenges on how do you get tolerancing to work and how can you get the kind of precision you need. So as a result, our program in our laboratory has become very expert in precision manufacturing. But it took, from 1960 to where we are now to come up with the National Ignition Facility. The pulse for the laser started in the core of the facility. It's a little tiny nanojoule pulse, and we amplify it, split it, and then we send it out and get to the target bay. I got a couple videos. I might want to do that one again. I don't know. It went faster than I thought it would. There we go. We took the top of the building off. The initial pulse starts in the middle. We take it out in fiber optics through a preamplifier into the main laser system. We're passing it back and forth in order to get gain in the laser. Then we go into what's called a switch yard, where we're just turning the beams to the target chamber and into the center of the target chamber itself. So you start with a nanojoule, and you get up to 1.8 megajoules. So that is, many, many orders of magnitudes of gain that we're getting through this system. Now 192 laser beams are going to come into this gold can called a hole room. It's like creating a little X-ray oven. The capsule in the center is the actual target. And you have a capsule wall with a certain type of material, and then both a solid tritium mix and a gaseous mix. The beams come in the top and the bottom. This is what we call indirect drive. We illuminate the walls of this gold can, which creates a plasma, right? That plasma then generates X-rays. It's like an X-ray bath. Time moves very slowly on my computer. And those X-rays then begin to bathe that capsule and create ablation of the surface of the capsule, right? So for every action, there's the equal and opposite reaction, right? So you're compressing that capsule. So you have that massive facility, right? 192 beams, 96 on the top, 96 on the bottom, coming in, illuminating the walls. Well, here's our capsule again. Once again, you got to remember this is about this big. Kind of hitting the walls. It happens faster. This is billionths of a second in real time. Create the X-ray oven. There we go. Ablate the surface, compression, and then of course the holy grail. We get to it, we actually achieve fusion. All right. This is the actual control room. Looks a lot like NASA. Got a whole team that sits there. I'll just talk through it again. So they just fired up the capacitor banks, which charged, illuminated the flash lamps. Here we are in the very front end, the master oscillator. This is our nanojoule pulse that we've created, and it's fully shaped. There's a lot of detail that goes into the actual pulse. We send it out into one of the two laser bays. It goes into the preamplifier modules, where we take it up to about 1 joule of energy. After that, we inject it up into the main laser system. And you're looking at 8 beams right now, what we call a bundle. We're passed it through the main amplifier, that pink glass, so as it passes back and forth through the amplifiers, the energy is increasing every single time. We use a relay optic system and telescopes, so you're seeing this, pulse of light. That pulse of light is about 15 feet long. It's a 15 nanosecond pulse. We take those bundles and come into a cluster, or 48 beams. There's 2 clusters to create 96 beams of lasers. Now we're going from the rectilinear coordinate system to a polar coordinate system. We're taking the beams and changing the direction to pick them onto the target. We're now doing the final, and we're going to go ahead and change the wavelength of the light from the 1053 to 351. Comes into the target chamber. Comes into that little tiny hole room. Once again, we're illuminating the walls, the can, we're creating the X-rays. Good, we're ablating the surface, creating the eventual burn. So that's all the really exciting stuff. I'm going to show you more pictures too. Good. You guys have the basic concept, a very large facility, 192 laser beams. There's a lot of symmetry that is involved here in this facility, a lot of reliability. There's tons of things I can talk about here. So I tried to take the kind of the intermediate level here and give you the basics of what this facility is like when you go into it. So how did we do that? How do you put together basically a $3.5 billion project? And then we actually did another phase for $1.5 billion. So this is a $5 billion asset for our country that we're talking about today. So significant investment. And how do you be good stewards of taxpayer dollars and achieve the kind of science that we need to achieve? And the way we did it is we followed what we call the first principles of project management in the project management body of knowledge, the PMBOK. I don't know if you guys are familiar with the Project Management Institute. Something you should become familiar with as you're studying engineering, science. You should understand project management because a lot of the work you will do will involve project management in one form or another. And the key principle when you want to put together a complex system, more than anything, is define the requirements. Anytime you think about a project or a deliverable, start with the requirements. What is it I have to deliver? And you know, our requirements were 1.8 megajoules of energy on target, 500 terawatts. You start at the highest level of defining your requirements, and then you flow all of those back through your system and break it into your subsystems. So key premise of project management is start, define your requirements, and you go through and you're going to plan your work. At this point, this is where you realize you have a lot of risks. And in a project like the National Ignition Facility, where it's more than a decade long, right? It was about 15 years to do those $5 billion. You're going to find a lot of technology risks. You're going to have to go into the project and say, I've got to develop technology in key areas because I know by the time I get to the end, that technology will have developed. So there's a whole risk analysis that goes into project management. Then you begin to work your plan. You constantly manage your baseline and your stakeholders, right? You're working your plan, you've got all of this lined out. And then the people that are paying the bills and the people that are waiting for your project, you're going to spend a lot of time talking to them as you're going through this kind of project, right? How are you doing and is it working? Which gets you into the lead and communicate, right? The National Ignition Facility had lots of challenges along the way. Highly political project for a variety of reasons. I went through a rebaselining. We started at 1.2 billion and rebaselined to 3.5 billion, and then held that baseline for over 10 years. So you can imagine the politics around that. There's all sorts of environmentalists and people who don't trust what our laboratory does. You know, we were called the RAD Lab. We were part of, you know, and we still are, the nuclear weapons. So we have environmentalists and others that like to protest. You know, there's the whole science community and competitiveness amongst the different types of science you can do. So managing all of that, yet delivering a project like the NIF took pretty significant skill and effort. Why do I show this? I just show the milestone schedule because it was what we established back when we went through rebaseline in 2001, and we actually achieved those milestones between 2001 and 2009. And embedded in here, and I'll bring it up a couple of times, were some of the areas of technology development that we had to engage. Speaking of politics, let's just walk through a little bit of the project. So we broke ground in 1997. We've got the director of the laboratory, Secretary of Energy, and one of our or Congresswoman Ellen Tauscher. So the politicians on a mass project, they'll show up in the beginning, right? So we've got groundbreaking. They show up at the end too, and I'll show you that next one. So we started here. It was a very large civil project. We moved 170,000 cubic meters of earth. Everything about the NIF is very large scale. You know, we went over 50 feet below grade, or about 85 feet above grade in part of the facility. We encountered interesting things along the way. You know, we were blessed to have the El Nino year. Right? California is in a massive drought right now. Let me tell you, it was not a massive drought when we were doing mass excavation. So I still remember Thanksgiving Day 1997, where I was on the construction site because it had rained 4 inches overnight, and makes for excitement. We also found at about 35 feet below grade an old riverbed where we found woolly mammoth bones. So it's not fun when you're, you know, pushing on your construction schedule and suddenly you find bones because you don't know where it could go, right? If they're human bones, that's a whole different issue than if they're, you know, mammoth bones. So we had a little cleanup site in the archaeological site. We have saved the bones and they are on display. But there was an ancient riverbed that ran underneath this facility and found all sorts of things. Goes into, remember the project management I was telling you about, what kind of risks, you know, there's known unknowns and unknown unknowns. You know, it's kind of falls in that category. So that is the, you know, kind of the conventional facility itself. This was about $300 million to build the facility. The facility actually has 2 fundamental components. The laser bay, the laser building, And this is one of the laser bays. I want you to remember this picture because I'm going to show it to you when it's full of hardware, right? This is, I kind of think of the laser as a utility. The laser physicists think that way, right? All I'm doing is I'm creating a nice utility because the target experimentalists and the target physicists down in the target area building, they're thinking about just how to use that utility to interact with their target and create data. They're the business end of the facility. So the laser bay is let's create the light that's necessary for the experiment. And in here, what you've got, that's about a 400-foot long laser bay, about 150 feet wide and 65 feet tall. That is a clean room. It's temperature stable to 65 degrees plus or minus a half. It's vibrationally stable, which is a real trick because if you're trying to flow mass amounts of air and have vibrational stability at the same time, that's difficult to do. All of the rotating equipment for the facility to, the lungs per se of the facility are up in the mechanical lofts to the right side of the screen. And here you have, all of your laser equipment about to sit here. So we created the world's largest optical bench. Those pedestals are sitting on a very isolated slab. It's about 4 feet thick, and we did it in a monolithic or continuous pour. So very stable platform, completely, to the best of our ability, decoupled from any vibration source in the facility. So one of our engineering challenges was making sure we did not impart vibration into the laser system. Lasers are very particular, right? They don't like vibration. They like temperature stability. Cleanliness is paramount for a laser system. The types of optics that we use, they're like getters. They absorb materials, any organic materials, and then you lose the transmissibility, right? And also laser light is energetic, extremely energetic, so even the tiniest particle, if it's sitting on the wall of your beam enclosure, it'll pop off and it'll land on an optic. You send light through it and suddenly you've blown up your optics. And there's over 25,000 optics in this system. So you don't want to do that. Cleanliness was a big deal for us. So there's a laser bay. This is where we're creating the utility. For each one of our laser bays, it's supported with capacitor bays. There's large pulsed power systems to go ahead and charge up and store the energy to dump into the flash lamps. Those are the flash lamps that excite the laser light, or the laser glass. So you've got a laser bay, you've got capacitor bays, you've got the laser glass itself. It's a very attractive pink color. It's actually really pretty glass. This was one of the technology developments we knew we needed to create when we started into the project, which is facilitizing our vendors. Of the $3.5 billion of the primary project, we contracted $1.8 billion of that to outside vendors. So we had to have very close partnerships, and we facilitized, or we got vendors to be capable to produce what we needed, and it was a joint effort. So because of the amount of glass that we needed, we had to facilitize a number of optics vendors to produce very large melts of laser glass. So that's what you're looking at. You're looking at an unfinished continuous melt of laser glass that we needed for the project. Another area of technology development is something called the plasma electropop cell. We call it the Pepsi. You noticed I showed you the, we come up with names for everything, and it's always cool when you're working on a project to have a piece of hardware named after you. So if you guys get into big project work like that, that's kind of fun. But so if I use acronyms, just tell me to stop and I'll tell you what I actually meant, because you don't know all my acronyms. You noticed when the laser light came up into the main laser system, we passed it back and forth a couple of times to get it through the glass, because we wanted to get gain. When we went into the project, we didn't know how we were going to capture that beam. You got to remember, you're down in nanoseconds. You've got a 15-foot long pulse of light. It's moving very, very rapidly. But we wanted to pass it multiple times through this amplifier glass, right? So that we could get gain in the laser. And we didn't know how we were going to do that, but we had a concept called a Pepsi. So this piece of hardware, if we couldn't have actually developed the technology, the facility would be literally 4 times as large, and it would have driven the cost of everything. So one more of our technology areas that we had to come up with going into the project. This is what the laser bay looks like now. Okay? Let me, right? That's what it looked like before. And then we filled it up with all of this. You know, the laser is a class 4 laser, which means it's going to damage your eyes, your skin. Also, the laser likes certain environments like high vacuum systems, clean, dry air, argon systems. So we have massive utility systems. What you're looking at here, this is just looking down literally the same laser bay. It's just populated with all of the enclosures for the laser. You're looking at like the exoskeleton of the laser itself. So think about all the mechanical engineering that went into this. This is a phenomenal engineering project. And it's actually all wired together, right, because it's got to have a brain, with over 30,000 cables and front-end processors. We've got 750 racks stuffed with equipment. We've got computer rooms, you name it. And you're seeing some of the cables here down the center of what we call the spine. So this is 96 of the beams. There's 48 on the right and 48 on the left. It's one laser bay. There are 2 laser bays for the facility, so you come up with 192. So by this point, once the laser light has gotten to kind of right below our feet, right, where we'd be standing, the light would come this way. It's going to turn into, you know, the light is perfect at that point as far as it's been amplified, it's been shaped. It's at the wavelength of 1053 nanometers, but other than that, it is exactly what we want. So the utility system has done what we wanted, and then we move into the business end of the facility. We get into the target bay. We're going to take those beams and we're going to switch them and get them onto the target. So this was another area of challenge. In order to change the wavelength of the light, we use crystals. And the crystal growth back when we started the project for this size crystal would take 2 to 3 years. But we needed a lot of crystals. You know, 192 beams, there's at least 3 crystals in each one of those beam systems. So we said, how could we do that? And we worked actually with a Russian scientist and several different vendors, came up with a technology, and we can grow a crystal of that scale. That crystal weighs over 800 pounds in about 3 months. And so you can imagine, you know, the chemical engineering, all of the different aspects of skills needed to come together and learn and create that kind of process. So once again, you know, what comes out of these mega projects? A lot of technology development. So we learned how to grow these crystals. And these crystals all will end up in the target chamber. So this is the target chamber, which that's about 10 meters in diameter. It's made out of aluminum. The walls are about 4 inches thick. You guys know what water towers look like, those big kind of can-looking structures. So we had a water tower. We put some air conditioning on it. We brought all the parts and pieces together, and we welded it. Then we machined it with all the ports. We brought out an 1,100-ton Ringer crane. We set it on the construction site. And on, this was very memorable for me. It was a Sunday morning at about 6 a.m. We picked, you don't want a lot of people around, honestly, when you're going to do this kind of pick. We picked that target chamber up out of the water tower and set it onto the site, and then we set it into the facility. So there was a phenomenal effort from the perspective of getting all this kind of integration, your rigging plans. You know, it's one of the fun things you get to do as an engineer. This is the chamber sitting into the facility. The target area building itself is all mass concrete. Our walls are anywhere from 6 to 12 feet thick. We do that because of the types of neutrons that we create, as well as the prompt doses of radiation. This is the inside of that target chamber. This was the cover of National Geographic magazine a few years ago. It doesn't look quite like that now. We put what's called a first wall structure. There's always stray laser light. You don't want to ablate the surface of that chamber, and then, you know, you got aluminum going places you don't want it. And also, you know, you'll have this beautiful target when you start, you know, very complex engineered device. After the lasers hit it, there's nothing left, right? So that all went somewhere, so we try and capture all of that. This is a view, that's the target chamber up there. Why does it look blue? So it started with aluminum, then we actually gunite it and coated it with about 16 inches of borated concrete. Once again, part of our shielding to help control the neutrons. These are beam tubes coming up. That's an assembly of 4 beams that is going up into the chamber. So you've got this chamber and you want your beams coming in the top and the bottom. And these are some of the beam tubes coming into the chamber. You could never take this picture. We had to kind of paste it together because there's floors in between. But you can once again see the chamber with the beams from the top and the bottom. This is where the wavelength conversion occurs, right here. It's something called our integrated optics module. There's over $800,000 of optics in every single one of those integrated optics modules. And there's 192 of them. So this is one of the most expensive places in our facility. And it's the place that damages the most, actually. So you've got this whole laser, right? You got all this great light. It's coming into this target chamber. You've seen all of that. But why do we do it? We do it to get data, right? So we have a whole suite of what's called target diagnostics. And these are X-ray cameras, they're interferometers, they're all sorts of different types. We've got 60-plus target diagnostics so that when we create an experimental plan, we do everything to define what we want the laser to do. We define the custom optics we might have at the very end, and then we say what's the data we want to get, and we configure a whole suite of target diagnostics around how to capture that data. So voila, we have the National Ignition Facility. We've got the politicians back. It's May 2009, which was the end or the dedication of the National Ignition Facility. So that was the first $3.5 billion. Our facility is operational. We're doing a lot of different experiments. We've, since the dedication, did another $1.5 billion set of projects in the facility. Now we're into, and that was completed in 2012, and now we're into day-to-day operations of the facility. All of the kind of work we did took partnering with other laboratories and industry along the way, a very, very collaborative activity to deliver this kind of facility, this kind of engineering and technology project. We are the largest scientific construction project successfully completed by the Department of Energy. If you guys know anything about the Department of Energy, you will know that project management is not their strong suit. Lots of challenges there. Our project did receive something called the Project Management Institute Project of the Year Award. We're extremely proud of this. Having gone through the first phase and doing the rebaseline and actually meeting every deliverable and giving back $1 million to the government on time was a big deal. So this was a very prestigious award that we received. So that's all exciting, right? And the results coming out of the facility, if you guys read Nature magazine at all, read the February 12th edition, and you will see some of the experimental results that we're achieving, where we are getting more energy out of the capsule than we've put in. So we're moving into, hopefully, a self-propagating plasma, and that will be a really big deal for us. So that's going great. But at the same time, great quote from Walt Disney, right? Around here, however, we don't look backwards for very long. I just looked backwards for you over about 18 years. But we got to keep moving forward, right? Opening up new doors, doing new things. We're curious, and curiosity leads us down many paths. And Secretary Chu, no longer our Secretary of Energy, but at the time, this was a quote that he came up with, which is, the National Ignition Facility is a marvel. We're going to achieve ignition. We haven't done it yet, but we need to be looking forward, right? And where should we be looking forward? And that's into fusion energy. Okay. So we're going to demonstrate in the National Ignition Facility the technology for fusion in the laboratory. Right now we've got the sun. We want to do that in our laboratory. And we want to do that for a whole variety of reasons, and one of them really has to do with our energy needs. And if you do just a simple comparison of equivalencies of needing 2 million tons of coal, which is equivalent to 1.3 million tons of oil, or 30 tons of uranium oxide, or just a very little bit of heavy water or deuterated water, which would be our fuel source for a laser-driven inertial fusion energy power plant. That kind of sounds cool, right? And you compare that. This comes from the Department of Energy. The electrical supply in the United States, right? What is this? This is our existing power plants, whether they're nuclear, coal, gas. What do we have, and when are they going to retire? Is this kind of bottom curve here, right? Where are we? We're sitting here. right? We're thinking everything's looking okay, but it's not, because our demand is growing. You know, everything we want to do with a larger middle class, there's a lot more demand for power. Our inventory is declining. We're going to be retiring a lot of the plants that we do have. So what have we got? We got a huge demand right here. And how can we fill that? Our thought is to create something called a life plant, where you take 384 lasers and you shoot a target at about 10 hertz. So you're firing your lasers 10 times a second at this target, which is a little bit of a different target, creating a fusion event every single time, which is going to generate significant neutrons. Those neutrons would interact with a flowing liquid, perhaps lithium, around, right? That's going to create a couple things. It's going to create a lot of heat. So you can go through a heat exchanger, and you can drive steam turbines with it, kind of a classic power plant. It'll also breed tritium, which is part of our fuel cycle, so we would have a closed-loop fuel cycle. So the concept is basically to take the lasers and 10 times a second fire that laser, so a high rep rate, hit the target, generate lots of neutrons, interact those neutrons with another material to create heat, and then just go through your standard power plant configuration. Something you couldn't tell by some of the slides I showed, the National Ignition Facility has a very firm architecture around reliability, and there's so many different components. What you do is we have a plug-and-play strategy. So we call them line replaceable units, where there's certain components, the optomechanical components that go into that beam path. You take it's like a size of a telephone booth would be one of these line replaceable units. You got a failed part, one of your bundles, you take this transporter out there, you dock it with your beam path, you take the broken piece out, you put the new piece in, right? The whole time your system's online, right? So you don't have downtime. The same concept using today's technology, because what I showed you was 1990s technology as far as the fundamental laser architecture using capacitors and flash lamps. Today we would use diodes. And by using diodes, you're able to shrink that whole laser system, which was, you know, hundreds of feet from start to end, down into a box that's about 10 meters long. So a key part of the concept around going forward is we demonstrate technology, or the technology in the National Ignition Facility for achieving fusion, and then we take those complex laser systems and we make them into what we call a line replaceable unit, a plug-and-play component. It's truckable. It will sit on the back of a semi, and therefore you don't need thousands of laser physicists hanging around, right? You put your laser in a box, and then you've got technicians and other types of workers that can interact with it. So maybe this was a little too fast. I can show it again. So this would be, quote, the life plant. You're looking at the top and bottom floors. That's all the lasers. This is what we call, quote, the life engine. You start sending the targets in. You fire the laser. You're around 10 hertz. You're generating, you know, you don't want to be there. This is like instant death to be in this area, right? That's also true in the NIF. If you're in the target bay during a high yield shot, it's a fatal dose of radiation. So there are hazards of that sort here. The thing about fusion energy is that the second you turn off the laser, there is no fusion, right? So it's a different type of situation than fission, which can have other safety implications. So here, you know, you turn your laser off and no more fusion. So our idea is an integrated plant. It's based directly upon the NIF performance. What we call the point design for the lasers themselves are very effective for the type of fusion we want. The modular factory built, this is the high plant availability. Remember I told you that with the NIF you can take a component out while your whole system is online. Similar concept here. Use of available materials technology, and it's got a great safety basis as far as what type of accidents could you have with that kind of plant, what would be the impacts to the surrounding neighborhood. You'd never find yourself in a situation where you have to evacuate the public. So it's got compact land use. You can put it on a fairly small site. Unlike nuclear power, it doesn't take the massive cooling towers. We could use the dry tower approach. a lot of water, carbon-free. I feel like I'm selling. It's just really interesting. I mean, the thoughts around, we've got to get to the point where we demonstrate ignition in the NIF, and we're working on that. And then how can we use this going forward? There are a lot of industrial partners. I got to tell you, when you start looking at those curves, right, and there's lots of studies going on right now. What are we going to do as a country, and what are we going to do as the world? I actually believe it's core to our national security, because if you have energy security, you actually have quite a leg on your national security. So with us leading the technology to find a better energy source will really make a difference for us. So significant interest. The partners that we worked with quite a bit on building the NIF are all highly engaged with us on what would it take if we wanted to do a laser inertial fusion energy plant. And they've kind of done these initial studies. That's where we are, is initial studies. So looking forward, it would be good, sustainable carbon-free source, safe base load electricity. I don't know if those are terms you guys are familiar with yet on looking at energy in the country, but base load is important. So security of supply, no enrichment, reprocessing, no high-level waste. We would end up with some activated materials which we would reprocess, but no long-term waste. That gets us into staying in touch with NIF. So that's the kind of the whole of my presentation around the National Ignition Facility, the project, as well as looking forward on how we could apply that technology into future energy needs for our country. We do have an app. If you have an iPhone, you go out to the store and look up NIF, and it's kind of cool. You'll get all sorts of pictures. You'll get the update on our experimental results, and there's videos. And we also have our lasers.gov website if you want to cruise around and see what else we have on the site. We do all sorts of work with lasers, high average power, short pulse, you name it, we do it. In addition to, the granddaddy here, this is a massive facility, but there's all sorts of other laser systems we've got. I've got some of our science and technology reviews if you guys are interested, some good reading materials, yeah, and some funny colored pens and some little brochures, so I've got some goodies. And I could take a couple questions, or you will tell me what happens next. So.
Yes, we got questions. All right. So, yes. This is very science fiction question, but what are the possible dangers and repercussions of essentially creating a miniature sun on Earth?
Okay, so you've got to understand the fuel source. We have such limited quantities of fuel that we're working with that there aren't hazards per se as far as creating a large-scale impact. So you limit the reaction with the amount of fuel that you have.
I'm just curious, with like all of that hardware and stuff that you have in there, what are the tolerances on that? Because you have very high tolerances.
That's right. So, for example, the alignment requirements to get the laser beams on the target are around 50 microns RMS. Okay, so the design started with the optical configuration, right? That's where the key design began for us. And from there, we did tolerancing from the optics to the optical mounts to the housings to the support structures to the facility, and worked to make sure that we assigned tolerances that were achievable for the industry that they were in. And so we have a precision network in the facility, so when we were setting equipment, we were setting it down, so it was a local network using laser trackers, right? So you couldn't use conventional surveying to get all the hardware in the right place. So there was a strategy behind how we did it. And frankly, we made mistakes in some places and put tolerances on, some of the construction tolerances just couldn't be achieved. So, yes?
With the laser and the precision that you were talking about and the precision that you achieved, how do you deal with small earthquakes that would maybe vibrate the facility and throw the laser off?
So we monitor it seismically, right? So we've got all sorts of seismic monitors out there to see what's happened. We've had like a 4.0 has been the largest that we felt, and it didn't affect us. It's kind of interesting. We do align the beams before every single shot. So we go through an alignment sequence. We're very sensitive to vibration real time. The freeway 580 is about 2 miles away, and we can feel that in our switch yards. So we can watch our beams depending on the traffic. So far, we have not had a seismic event that's created an issue for us. The design requirements for the facility, because of the value of the asset, were much more stringent when it came to seismic. You know, our joke is if there's an earthquake, run to the NIF, because it's going to be one of the safest places to be. Yes?
If you included the charging of capacitors, how long did it take from the initial starting to your finish when you explode the charger?
Including or excluding?
Including.
Okay, so the charging the capacitors is 30 minutes, and it dwarfs absolutely everything else. From the start to the finish is probably, it's just maybe 20, 30 billionths of a second. I mean, it's yeah, from the, so the really long is the charging and also the setup for the shot, right? So it takes us a good 4 hours to set up for a shot, to get the target in its place, to do pre-alignment, you know, to get everything ready to go, then charge the capacitors. And so it's extremely anticlimactic. I hate to break the news. You know, I showed you that, the good music in the control room. It sounded dramatic, right? And that's like watching paint dry. You know, you start the shot sequence and, oh, it's over. It's just
You could achieve that with your system.
the high rep rate. Yes. One of the things that we work on at Livermore is high rep rate lasers, and we know we can get well above 10 hertz, over 60 hertz actually. So, yes. I think the key for us, one of the keys will be the cooling, keeping the amplifier slabs cool enough that you don't get wavefront distortion. So we've been working on some helium cooling systems around that. So, yes, I think we can get there. Yes?
You said that y'all guys like to name things.
Mm-hmm.
Is there anything named after you?
You know, I've been there all that time, and not that they tell me anyway.